Okay, so we're going to look to represent a plane in the vector equation. Just like with lines, there are different forms, and we will go on to look at those with the vector equation of a plane. So we get planes in, we're still looking at R3. This is an X coordinate axis, Y axis, and the Z axis. Some plane, they look sort of like this. Okay, so this is what our plane will look like. Of course, this plane would go on forever in all directions, so it would keep extending this way, this way, this way, and now it's just impossible to draw. Okay, so exactly like the vector equation of a plane, we're looking to specify this plane by writing a formula out for a generic point on the plane. So what we want to do is say we want to write that any r on this plane, any vector r that finds itself on this plane, satisfies some equation. And that way we've specified the entire plane, because it can't be the different plane if all r on this line satisfy the equation and every r that satisfies the equation is on this plane. So if we have a generic point r here, so this r, r is equal to, again we have an a. An a is just any vector. I don't know what's going on with this graphics pen today. Anyway, a is just some vector that gets us onto the plane. Okay, so from the origin, we had the exact same thing. Vector equation of a line. So now we have mu, and we'll call this vector b, and then we have lambda, and then plus mu c. And why do we specify two vectors here? Well, any two vectors that are non-parallel with each other. Okay, so this could be b and this could be c. The color. And this could be c. And the point is that they have to be non-parallel, and if they're non-parallel, we can use them once we're on the plane to cycle to any point in the plane. Okay, because we can, from A to get to I, we can go a certain amount of B's, maybe back a little bit. So maybe we'd go negative B a couple of times, and then a certain amount of C would get us to that point. And we can do that for any point on the plane. So that's our equation. I want to talk about this. When we say P and C are on the plane, it means that once we're on the plane, they keep us on the plane. That means they run parallel to the plane. Okay, they both run parallel to the plane in the sense that, like I say, if you're on it, you stay on the plane. So that's pretty much it for the vector equation of the plane. Not a particularly complicated formula. If you understood the vector equation of a line, then this should make sense. Our future definitions of planes come from sort of the normals to the plane and stuff, and we will look at those in the next ones. As I was saying, perhaps some of those are a little bit more useful in calculations, but this one is a nice introduction, and hopefully you can see the analogues between this and the vector equation of a line, like I say. But if you do have any questions, let me know down in the comment section below. If you did enjoy the video, please be sure to like the video and subscribe to the channel if you want to see daily maths tutorials. Now that's it, and I hope to see you in the next one. Thanks for watching.